Hi, let's now explore the rationale behind optimal power flow calculation. In this lecture, we describe the key elements and the structure of the optimal power flow problem. Optimal power flow is an optimization problem that determines the best operating point of a power system by minimizing or maximizing an objective function, typically generation cost or losses, while satisfying power flow equations and operational constraints. The inputs of optimal power flow usually consist of network data like buses, lines, transformers, compensation, storage, etc. Generator, limits, cost, load demands, profile, limits, cost, and system technical constraints. The ranges for adjusting the set points of controllable assets define the bounds of the control or optimization variables for the search of the optimal or near to optimal solution. Finding the optimal value means identifying the set of control variables like generator outputs, set points of compensation devices that yields the best objective value while keeping the system physically feasible and secure. The applications of optimal power flow include operation, for instance, economic dispatch, congestion management, voltage control, loss minimization, and also planning, for instance, network expansion, placement of generation or reactive support, integration of renewables. Typical optimal power formats consider single objective or multi-objective structures, which can involve the steady state, most common approaches, or dynamic system model. Mathematically, the degree of complexity can be associated with nonlinear and non-convex formulations, which become more complex if probabilities and multiple scenarios are considered instead of a deterministic single scenario. Analytically, it is possible to write a generalized form of an optimization problem. Here we have an objective function, which is the first thing we have to define. Then we need the constraints and the boundaries for each variable, which is part of the so-called solution vector. Let's discuss this from bottom to top. A solution vector X is the set of values for our variables that allows us to reach our goal. This, the solution of our optimization problem. Each of these variables, of course, have a minimum and a maximum boundary. These boundaries come from known data. For instance, if one of our variables is setting the output power of a certain generator in the network, then it is easy. The maximum and minimum possible outputs of any sort of generator is a well-documented value. Now, of course, you probably can operate this generator at the limits when it is in a certain network. For instance, because of thermal constraints of the cables in that zone. This is the technical constraints part. There are two types of such limits: inequality constraints and equality constraint. An example of inequality constraint was just given, that of a thermal limit. That means that a certain variable in your calculations need to be less than or equal to a certain value. The other type of constraints is the equality. This could be, for instance, the nodal balance, meaning that the sum of power at a node which should be zero, as the power flowing into the node should equal the power flowing out of it. This is an example of a combination of variables that undoubtedly must be equal to an exact value. And lastly, the objective function. What you see here is the most generalized form. It is a summation of different functions with weights associated to each of them, providing you with a simplified multi-objective problem as a single objective problem. In this course, we will work with single objective optimization, but it's good to be aware that this is only one of the many possible approaches. The optimal power flow problems appears in multiple formats depending on modeling choices and practical needs. It can be single objective, for instance, cost minimization, or multi-objective, for instance, cost, emissions, and losses. Theoretically, it can be unconstrained for preliminary assessment, However, it is inherently constrained, since physical laws and operational limits must always be satisfied. Decision variables are often continuous, like voltages, power outputs. Yet many realistic formulations become mixed integer, for instance, unit commitment switching, and occasionally combinatorially when discrete decisions dominate. From a complexity perspective, optimal power flow is challenging due to its high dimensionality in large networks, strong nonlinearity from power flow equations, and pronounced non-convexity, which leads to multiple local optima, that is the so-called multimodality. Additional difficulties arise from possible discontinuities, for instance, switching actions, the need for accurate modeling of a physical behavior, and the resultant computational burden, especially in multi-scenario and real-time applications. Let's now visualize more or less how such a space looks like. Imagine this is a multidimensional space, which for the sake of simplicity, we are looking at it in 2D. The surface is defined by all the optimization variable boundaries between a minimum and a maximum for each of them. We also have some constraints, so the feasible solution can actually lie only in certain regions of this search space, like what we see here in the blue regions in what we call the feasible space. The other regions within the border and in Y are still part of the search space and can have an optimum in them, but they encompass infeasible solutions due to constraint violation. For instance, a solution that requires more power than what you generated can physically deliver. Typically, you start by giving a guess for one optimization variable. So you might, from that, generate an initial value between the minimum and maximum boundaries for each of the elements of the optimization vector. If you are lucky, it might already be in the feasible space, but it could also be in the infeasible space. You see, the less knowledge you have or your constraints, the more difficult it will be to solve the problem, because you don't have any certainty on how feasible this set of variables altogether will leave you in terms of the boundary and technical constraints. This is why your optimization algorithm has to be good enough to make the solution move throughout the search space until it finds the feasible optimal value. This is the basic task of an optimization algorithm: to start from your initial guess of variables and find the right direction for iterating each of the optimization variables to convert towards the optimum. This is an example of how the solution of the particles could look like. As you see, there are multiple solutions, some of which feasible, some not, and one would be the global optimum solution. For example, if you are looking for an operating cost of less than 5 million euros per period, you could find many feasible combinations that gives you, for instance, solutions of 3.4, 4.8, and 4.3 million. This all satisfies the constraints, but that of 3.4 million could be assumed as the near to global optimum. The most classical solving method is to start with one solution and try to find the direction of search through derivative values of the variables to move towards the optimum solution. So one solution moves you towards a more optimum solution. But with what is called the meta-heuristic approach, you can have more than one solution all over your search space, which you might run, or you might even sample randomly each variable between the minimum and maximum bounds and then run the algorithm. This way, you have many solutions spread around, and that converges towards your optimum. This way, you have a chance of finding the optimum quickly. It is important to be familiar with the terminology that we have just introduced, as we use this jargon in this topic, especially the word particles, which basically means the solution vector. This concludes our video, where you have learned about how to define and tackle an optimal power flow optimization problem. We also learned how one or multiple GET solutions can be used to go through the search space to find the optimal solution for your objective function. Thank you for watching.